The normal distribution describes many real-life data sets. This histogram, we're going to let
alludes to
mu
the shape
be the
of a
mean,
normal distribution,
and sigma
histogram
be the standard
represents
deviation
discrete data
for our distribution. A normal distribution represents continuous data. This curve is continuous. Let's look at some of the properties of the normal distribution. Before we start, just keep in mind that we'll use the symbol mu for the population mean, and we'll use the symbol sigma for the standard deviation of the population. A normal curve is said to be bell-shaped, shaped sort of like a bell. The highest point on that curve occurs at the mean mu. It turns out that for a normal distribution, the mean, median, mode are always equal to each other, but we'll only be using the mean. But just keep in mind the mean, median, mode are really the same for a normal distribution. The curve is symmetric with respect to the mean. If you drew this curve on paper and folded it along the vertical line through the mean, the left half would fall right on top of the right half. The total area under a normal curve is 1. If you added up all the area under a normal curve, you would get 1. Roughly 68% of the data values are within one standard deviation of the mean. So if you went out one standard deviation to the left and one standard deviation to the right, you would have about 68% of the data values. However, if you go 2 standard deviations out from the mean, if you go to the left 2 standard deviations and to the right 2 standard deviations, you would have about 95% of the data within that range. And finally, if you go 3 standard deviations from the mean, you've got almost everything. So if you go out 1, 2, 3 to the left and 1, 2, 3 to the right, you've got virtually everything. Notice this curve never actually touches the axis. So you never get it all, but by going out 3, you've got virtually all of the area. This is called the 68, 95, 99.7 rule for normal distributions. It tells you approximately what percent of the data values lie within 1, 2, or 3 standard deviations of the mean. That's going to be important, so you need to learn those 3 numbers. Let's look at a problem. This problem says the distribution of scores of 1,000 students on an intelligence test is a normal distribution with mean 450 and standard deviation 25. The question is, what percent of scores would be expected to fall between 425 and 475? Obviously, to answer that question, we need the 68, 95, 99.7 rule. So you need to start thinking about how you're going to keep that in mind, memorize it, or learn it well enough to remember those 3 numbers, 68%, 95%, 99.7%. You're going to have those for all of these problems. Now that you got that, think about, or actually maybe even sketch out, the normal distribution. They're asking about values that fall between 425 and 475, so you'd want to put those into your sketch. And the whole reason this works for us is that the shaded area gives us the probability, which represents the percent that we're looking for. So the shaded area on this curve is the probability of having a score fall in the 425, 475 range. And that will be the answer to our question. So how do we do that? It all involves dealing with the mean and the standard deviation. So let's put those on the graph. The mean is 450. The mean always occurs at the highest point on the curve, so there's the mean. They're asking about 425 and 475, and we've got to figure out what those numbers have to do with that standard deviation of 25. And here's how we do that. We look at the difference between the mean and those 2 numbers. So finding the difference involves subtraction. So we say 450 minus 425 is 25. And also notice that if you do it the other way, go from the other endpoint, 475 to 450, you also get 25. So what we've discovered is that if you put the mean on the graph and go 25 units to the left and 25 units to the right, which is a standard deviation, in fact it's one standard deviation from the mean, you have that exact orange shaded area. What that tells you is the piece of information that you need to isolate the part of the 68, 95, 99.7 rule to use. If you know that you're one standard deviation away from the mean, that tells you that you're going to use the first line of the 68, 95, 99.7 rule, which says that 68% of the values are in that orange shaded area. And remember, that probability is the percentage of scores that we're looking for. So that tells us that about 68% of the scores should fall between those two. And sometimes that's all the question asks. I'm actually going to add a second question. I want to see why you might actually use the piece of information that we didn't use earlier. We're told that there are 1,000 students taking this, and we didn't use that piece of information. And the reason is we didn't need it just to find the percent of scores. But if I change the question, that 1,000 students number becomes important. So I'm going to change the question slightly from what percent of scores would be expected in that range to how many of the 1,000 scores would be expected to be in that range. Now think about the difference. The first question asks about a probability or a percent. This question asks for an actual number of student scores. Well, how do we do that? Once you've done the percent part, this part is really easy because you already know that 68% of those scores are going to lie in that interval. So all you have to do is take 68% of however many student scores there are. If there are 1,000, you use 1,000. If there are 632, you'd use 632. In this case, there are 1,000 student scores, so I'll take 68% of 1,000. 68% is 0.68. 0.68 times 1,000 is 680. So to answer the second question, we would expect about 680 of those 1,000 student scores to be in that 425 to 475 range. Let's look at another. The distribution of scores of 1,000 students on an intelligence test is a normal distribution with mean of 450 and standard deviation 25. What percent of the scores would be expected to fall above 500? I hope you recognize that this is exactly the same situation, only the final question changed a little bit. The mean is still 450, just like it was previously. The standard deviation is still 25, as it was in the previous problem. The question changed. Now we're asking what percent of scores would be expected to fall above 500. So if we think about it, the 450 mean goes on just as before, but now we're not interested in a percent between, we're looking at a percent above 500. So if you look at it on the graph, we're looking at that. The orange shaded area is the percent that we are interested in. So we proceed just as before, which means we need to find out how many standard deviations 500 is from the mean. We want to see how far it is from 500 to 450 measured in standard deviations. That involves finding, first of all, how far apart is 500 from 450, and that comes out to be 50. So you got to say, well, how many standard deviations is that? Well, the standard deviation is 25. 50 is 25 plus 25, so that means it's 2 standard deviations. So 500 is 2 standard deviations from the mean. That tells us which line of the 68, 95, 99, 7 rule to use. In this case, we're looking at the one that talks about being within 2 standard deviations of the mean. What it says is 95% of the values are within 2 standard deviations of the mean. Now, look at that on the graph. 2 standard deviations from the mean doesn't mean just to the right. It means either direction. So if you go 50, which is 2 standard deviations to the right, of course you get to the 500. We know that. But you also have to look to the left as well. But if you take 50 from 450, you get 400. So what this rule tells us is that 95% of the values lie between 400 and 500. That's not exactly what we're looking for, though. We're looking for this little piece of area over here. So even though that rule didn't give us a percentage directly, it did give us enough information to figure out what we do need. We need this area right in here. How do we get it? Well, if 95% of the area is between 400 and 450, that leaves 5% unaccounted for. But that 5% has to be split between the left tail and the right tail. But we know this distribution is symmetric. We know normal distributions are always symmetric. That was one of the properties. So that means that half goes on the left and half goes on the right. Half of 5% is 2.5%. That means that 2.5% is going to go here, and 2.5% will go there. Now you can see that the shaded area represents an area that's 2.5% of the total area. So about 2.5% of the scores should be above 500. Think about how you did that. The flow of the problem is about the same in either case, but you have to look exactly at the question to figure out which part of the area you need. And as before, if I want to ask an additional question that actually involves knowing the number of students, or the number of student scores I should say, I could change the question from what percent of scores to how many scores will we expect to be above 500. And as before, once you get the percentage, the other part's easy. It's just 2.5% of 1,000, or 2.5% of whatever that number happens to be. So you take 2.5% of 1,000. Well, 2.5% is 0.025. 0.025 times 1,000 is 25. So to answer the second question, we would expect about 25 of those 1,000 student scores to be above 500. You can simplify this procedure somewhat by noticing the patterns, because once you know the number of standard deviations away, those percentages are fixed. And I'll show you what I mean. When the endpoints are one standard deviation from the mean, you've got 68% of the scores within one standard deviation, and that 68 gets split into half, which would be 34 and 34 around the mean, and then you've got some left in the tails, and it turns out there's 16% in the left tail and 16% in the right tail, and of course if you add up all of these numbers you get 100%. That's the way the percentages break up if you're one standard deviation from the mean. If you're two standard deviations from the mean, you get 95% of the scores in here. That 95% is cut in half at the mean, so that means 47.5% to the left, 47.5% to the right, not counting the tails. That leaves another 5% to be split between the tails. So that tells you that 2.5 go on the left tail and 2.5% goes on the right tail. And again, if you add up all these numbers, you've got your entire 100%. That's the way the percentages break up when you are two standard deviations from the mean. When you're three standard deviations from the mean, you get 99.7% of the scores between those two endpoints. If you half that, that gives you 49.85% here and 49.85% here, and that only leaves you 0.3 to distribute half and half, and if you half 0.3 you get 0.15%. So those are the breakdowns if you are three standard deviations from the mean. So in summary, if you know how many standard deviations you are from the mean, you also know the percentages that are going to pop into the problem. You can work them from scratch and sort of figure them out as you go, or if you want, you can memorize those three sets of percentages, and that might speed you along when you're working the problem. It's totally up to you. Let's look at this example. It says the distribution of scores of 1,000 students on an intelligence test is a normal distribution with a mean of 450 and a standard deviation of 25. How many scores do we expect to fall below 375? Now this is a problem we've worked several times now. I keep changing the final question, but everything else is the same. We have 1,000 students. We've got a mean of 450. The standard deviation is 25. We're looking for the number of scores we expect to fall below 375. So if you put 375 on the graph, we're looking for the numbers below that. So it's the same game as before. We need to find out how many standard deviations there are from that number to that number. Do it by subtraction. 450 minus 375 is 75. The standard deviation is 25. 25 times 3 is 75, or 25 plus 25 plus 25 is 75, whichever way you want to think about it. That tells us that 375 is 3 standard deviations from the mean. That's what we needed to know. That tells us which line of the rule to use. So now we know we want to use the third line of the rule, the one for being 3 standard deviations from the mean, and that's 99.7. This time, instead of doing it ad hoc, let's actually take advantage of that summary sheet I developed. The summary sheet tells me for each case, and I know now that I'm at 3 standard deviations away from the mean, so I know these numbers I've circled are my percentages. If I take advantage of that, I can sort of match it up. I can see this matches to that, and that immediately tells me what my percentage is. So the orange area is 0.15%. And since I have 1,000 student scores, I simply take 0.15% times 1,000. Remember, to change the percent to a decimal, I'll move the decimal 2 places to the left, so that becomes 0.0015. And if I multiply that by 1,000, I get 1.5. So we expect about 1.5 scores to be below 375. You can sort of see how learning those numbers might shortcut your work a little bit. But again, it's up to you whether you want to do it that way or not. Here's another one. The distribution of scores of 2,000 students. I've been working with 1,000 students. That made the arithmetic really nice. But it doesn't have to be the same. I'm going to 2,000 students this time. The distribution of scores of 2,000 students on an intelligence test is a normal distribution with a mean of 150 and a standard deviation of 10. How many scores do we expect to fall between 150 and 180? I hope by now you're into the flow of it and you know what you have to do. Let's see if we can do this just as efficiently as possible. We're going to draw the normal curve. We're going to put the information on it that we know, and we're going to figure out which line of the 68, 95, 99.7 rule applies. To do that, we've got to figure out the difference between the mean and the 180 and change that to standard deviations. Of course, 180 minus 150 is 30. The standard deviation is 10. There are 3 tens inside of 30, so we're looking at the third line because 180 is 3 standard deviations from the mean. Once we know that we're looking at the 99.7% line at the table, and if you've learned these numbers, you're a step ahead. These are the percentages that will apply to this problem. We know the mean is 150. 180 is 30 units to the right of the mean. So we're looking for the number in between, which is 49.85%. So 49.85% of the value should be between 150 and 180. But this time we're working with 2,000 student scores. So we take 2,000 times 49.85%, change the 49.85% to a decimal, multiply by 2,000, and you'll come up with 997. So we expect about 997 scores to be between 150 and 180. Let's do another. A normal distribution has a mean of 36 and a standard deviation of 5. What percentage of values do we expect to be below 26? I've been trying to use the knowledge we've built up to make things work as efficiently as possible. I'm going to try to make that even more so here. Let's try to do this absolutely as efficiently as we can. The first thing we want to do, we've done several of these problems, the first thing we always want to do is find the difference between the mean and the value they ask about. The value they ask about here is 26. The difference is 10. We want to change that to standard deviations. The standard deviation is 5. That's 2 standard deviations. 5 plus 5 is 10. There are 2 standard deviations inside of 10. So that tells us we're using the middle line for our rule. And if we've learned those numbers, we know the percentages for that middle line. And now we just want to find the percent that goes below 26. Well, remember, the 26 is on the left, the far left, so the number that's going to be below that will be related to 2.5%. The final step will be to say that about 2.5% of the values will be below 26. Might not be a bad idea to go back through these one more time and just see the patterns and see how they all work out just about the same. There's some slight differences between asking below something, above something, or between something, but the procedure is basically the same each time. Go back through them again and make sure you see the flow. Once you get that flow, you can work any of these problems pretty much the same way.